Hello viewers, I welcome you all to this online pre-recorded videos on electromagnetic waves, Module 2, Class 6. In this video, we'll be discussing about potential gradients and dipoles. We have discussed two methods of determining potential in our previous video. So here, we'll be directly discussing about the electric field intensity by means of a line integral and basic volume charge distribution with volume integral. But in practical problems, however, we rarely know electric field or volume charge density. So preliminary information is much more likely to consist a description of equipotential surface. That means potential is equal on the entire surface. And the goal is to find the electric field intensity. So here we are trying to establish a relationship between electric field intensity with a potential gradient. So the general line integral relationship between V and E is established as V is equal to minus integral E dot dl. Therefore, dV is equal to minus E dot dl. For a very short element of length delta L, E is essentially constant for a small length delta L. Therefore, delta V B minus E dot dl. Delta V is equal to minus E dot dl. Therefore, delta V by delta L equal to minus E cos theta. If we try to understand scalar or dot product expansion of A dot B is equal to AB cos theta. Similarly, delta V by delta L is equal to minus E cos theta. Assuming a conservative field, the result of the integration is a function of the endpoint xyz. We may try to limit and obtain the following equation: dV by dl is equal to minus E cos theta. Therefore, potential gradient, the maximum positive incremental of potential delta V max will occur at cos theta equal to minus 1. Therefore, dV by dl max is equal to E. We can now conclude two characteristics of the relationship between E and V at any point is given by its maximum value of the rate of change of V with distance L, and secondly, the maximum value of V is obtained when the direction of the distance increment is opposite to E, that is minus delta V. Therefore, I can obtain the equation E is equal to minus dV by dl to the max, which can be written as E is equal to minus dV by dN normal to the direction. Hence, we can come to the conclusion the mathematical operation to find the rate of change in a certain direction is called a gradient. So in general, gradient of T, where T is a scalar field, can be defined as grad T is equal to dt by dN normal to the direction. Therefore, E is equal to minus dV by dN an, which is equal to minus grad V. It's called as potential gradient. Since V is a function of x, y, z, the total differential equation is given by dV is equal to dou V by dou x dx plus dou V by dou y dy plus dou V by dou z dz. And we also know dV is equal to minus E dot dl. Therefore, minus Ex dx minus Ey dy minus Ez dz. Both the expressions are true. Thus, grad V is equal to dV by dx ax plus dV by ay dy plus dou V by dou z az. Now, gradient of scalar is known as a vector quantity. We know potential gradient del V is given by, for rectangular coordinate system, for cylindrical coordinate system, and for spherical coordinate system in terms of AR, A theta, and A phi. Let us have a simple example to calculate EV, that is potential and electric field and electric flux density, and along with rho V. Given the potential field V is equal to 2x square y minus 5z. Therefore, V is given by substituting the values of a point x, y, z. So the V is given by, V at point P is given by 66 volts. In order to calculate E is equal to minus del V, that is grad V. It's given by dou V by dou x AX plus dou V by dou y AY plus dou V by dou Z AZ, which is equal to minus 4xy AX minus 2x square AY plus 5AZ. Therefore, electric field at point P is given by 48 AX minus 32 AY plus 5 AZ volts per meter. The direction of E can be found as A is equal to vector over its magnitude, which is equal to 525 AX minus 283 AY plus 44.2 AZ picocoulomb per meter cube. Rho V is equal to divergence of D, which is given by divergence of epsilon naught E, which is equal to minus 35.42 Y picocoulomb per meter cube. But at P, Y is equal to 3. Therefore, rho V can be obtained as minus 106.26 picocoulomb per meter cube. Now, in this slide, we'll try to explain what is the dipole. The dipole fields form the basis of the behavior of dielectric materials in electric field. The dipole will be discussed, which will serve as an illustration about the importance of the potential concept presented previously. An electric dipole, or simply a dipole, is the name given to two point charges of equal magnitude and opposite sign, separated by a distance, which is compared to the distance to the point P at which we want to know the electric and potential fields, just like plus Q1 minus Q1 or Q2. So therefore, electric flux leaves from plus Q1 and reaches minus Q2. So plus Q1 and minus Q2 are represented as two electric dipoles. Plus Q and minus Q here in this example slide. So the total potential at P can be written as Q over 4 pi epsilon naught 1 over R1 minus 1 over R2. In general, the dipole is given by, the dipole potential is given by V is equal to QD cos theta over 4 pi epsilon naught R square. Using the gradient in spherical coordinate system, we will obtain E is equal to QD by 4 pi epsilon naught R cube of 2 cos theta AR minus sin theta A theta. Thank you for watching this video.